Okay, so good evening. I will present today some preliminary results on a work in collaboration with Alex concerning the entropy cascade theory in gyrokinetics. We had a number of talks about, and the idea was to use a full Vlasov approach in order to understand better about the applicability of this theory. So very rapidly, I will remember you, but I mean, we had a number of talk about the gyrokinetic orders and what does it mean, the entropy cascade, and then we will step on the hypothesis of the Vlasov approach. I will rapidly review the linear theory and spend a few words about the Bernstein-Landau paradox, and then present the results of a number of Vlasov simulation on this problem. So as we already heard, the gyrokinetic approach is based on an expansion in small parameter epsilon, and low frequency fluctuations, and particularly much less, the regime is where omega is much less than the ion cyclotron frequency. And then obviously we are the approximation is we have the quasi-neutrality. So we already see that by integrating the gyrokinetic equation, it's possible to obtain a generalized energy, which is an invariant on the system, and in particular we can obtain the gyrokinetic distribution function, which Steve Coley have discussed in his first talk, and then we had some other talks about. And the idea is that this energy is transferred to the larger scale via a nonlinear cascade, which happens both in the physical and in the velocity space. So the limit is that we consider k perp which are larger than 1 over rho, and in particular we will use the electrostatic approximation, at least as a first approach. Okay, so in this limit the generalized energy becomes proportional to the perturber part of the entropy of the system, so that's why it is known as the entropy cascade. Okay, we will see the potential component here. This is in general can be neglected. Yes, in this development, if I remember well, is more. Yes, it's negligible.
Very small. Because of the Bessel function.
Okay. In a numerical code, it's not going to, right, okay.
No, in a numerical code, in principle, there is, because we have the Vlasov approach, so we have everything. So, okay, so entropy cascade, and now by ruling out the analytical theory, it can be shown that by defining the electric field spectrum and the density spectrum, the power law are the following: minus 4/3 for the electric field and minus 10/3 for the density spectrum, where the density and electric spectrum are defined in the usual way. Okay, and I mean we based our work on some 2D simulation using the gyrokinetics approach obtained by Tatsuno in 2009. that confirm this scaling in the range k rho I between 1 and 100, which is the part that where the entropy cascade is valid.
Minor question, one page back.
Yes.
Is SE the spectrum of the phi square or K phi square?
Is delta
Of the SE,
S is the electric field.
the electric field.
Electric field.
K5.
So K, yes, K fine. Electric field is full electric field.
If you add 6, you get minus 10 for
That's very, yes, it's
Yeah.
So the Vlasov-hybrid model. So we are in the 2D approximation as Tatsuno, physical and two-dimensional in space. In the electrostatic limit, we assume that we have quasi-neutrality and we use kinetic ions. So we solve the full Vlasov equation for the ions in 2D-2V with fluid massless electrons with an isothermal closure. So this means that we have to solve the Vlasov equation for the ion distribution function, okay, for the full Vlasov distribution function, and the closure is given by the essentially a Boltzmannian response of the electrons. Okay, so the electric field and the density are easily connected by this equation. Now, linear theory of this Vlasov electrostatic model. The linear theory of the full Vlasov equation showed that the linear modes are the ion Burston waves, okay, as is quite known, and obviously these are out of range, so not in the gyrokinetic theory. And the interest is that these waves can modify the development of the entropy cascade due to the Bernstein-Landau paradox. So now more or less I think everybody knows about the electron Bernstein-Landau paradox between electron Bernstein waves and plasma waves. The same things happens between the ion Bernstein waves and the acoustic waves, because in principle the ion Bernstein waves are not damped, but if you think that the limit of zero magnetic field are the corresponding ion acoustic wave and there is a damping, when the point is that in the transition between the regime where the mode is I mean the gyro frequency is large, so the acoustic part is negligible, there is no damping, but in the limit of zero magnetic field, then there must be some damping. And okay, and this kind of problems be studied in the electron case by Valentini a few years ago. And the important thing is that I mean, if the in this regime the Landau damping rate is not too small compared to the gyro frequency, then you can have some damping, so some absorption of the energy, and then obviously the system can react in a completely different way from what we expect. So this is the result is a simple plot. Here there is time normalized to ion cyclotron frequency. Here is the amplitude of the initial, we put initial amplitude of a given wavelength. What you see is that since we are now in the limit where the damping rate is larger than the gyro frequency, what happens is that even if the magnetic field is not zero, so formally the ion Bernstein wave should have no damping, there is some damping, okay? So the wave is rapidly damping by Landau, but it comes back in phase after 1 gyro period, so in our units is 2 pi, okay? And so you see that recovery of the waves, and then dampened again, and then recovery, and dampened again, and recovery. one thing that we have to
Just the overall damping is probably numerical.
yes, that was exactly what I was saying. And one thing that we have not studied, but I think that's more or less clear, is that you see that the amplitude here is decreasing. But this decreases that, due to Landau damping, you reach the grid scale of the code, and there you need some numerical dissipation. So you lose some part of the initial energy. So in principle, if you have a fantastic grid resolution, you should recover more or less the same amplitude, because there is no reason, in principle, the system is Hamiltonian, so you should recover all the initial energy, okay? So this is illustrate that your waves is absorbed and re-emitted, so this is typical of the regime we are exploring.
This
So
depends on how you initialized.
absolutely.
Initialized
It depends on the value of your k rho I. If k rho I,
But even at a fixed k rho I, your initial perturbation, you've got a lot of flexibility in that distribution function.
if the
somehow be avoided just in the initial condition.
no, it depends. Yes, but for example, I will show you if the temperature of the electron temperature is very large. Okay, there is no Landau damping, and so in this figure you will have no absorption. So we have just the wave fluctuating, etc. Or if your gyro frequency is very strong, then you will have no absorption because you have no time to absorb the wave by Landau damping. Okay.
What would the frequency of that wave be?
You have to compare more or less the ion cyclone frequency with the corresponding Landau damping rate of the acoustic wave with the same wavelength. Okay, so it's but I have a slide on this.
There are dry kinetic oscillations at k per rho equal to 3, whose frequency is much less than the ion acoustic wave frequency at that same k.
Yeah.
Yes, exactly.
And so somehow, okay, so we should go on. This is something
He's
to consider
good. I
later.
think at the end he takes out these and only looks at those.
Well, but presumably any initial perturbation will split itself into everything,
Right.
and some of it will be low frequency. At least that's what we thought when we started with this. Some of it will be low frequency, and that will do the gyrokinetic thing.
Sure.
And the high frequencies will do the high frequency thing.
And there
the
will
issue
be-
was can they talk to
exactly.
each other?
Some response, in principle, you can have some response at high frequency and some response at low frequency. It can depend on your initial perturbation. Well, so we define gamma dissipation, the Landau damping rate, which is dissipation in some sense, because formally you don't, you can always recover this energy. So we consider the limit where the gamma is much larger than the cyclone frequency. Okay, so this corresponds more or less to the zero magnetic field limit. Okay, and in this case, as I will show you, the energy cascade is inhibited. So this is the result of a simulation. Here is k rho I from 1 to 100 and more, but let's say the regime is 100. Here is the initial spectrum. In this case, we put a flat spectrum on density, so the electric field is going, but we have other simulation where we put a decreasing spectrum on the density, and the results I will show you are more or less the same. So if we let the simulation go, then you see that your energy, you see that you have something at the initial. we thought that there was something wrong with the code because the energy seems to be absorbed, but then it comes back again and then down and back again. So after 60 periods, there is no sign of cascade. So in principle, what we do is we put some energy on some initial wavelengths, okay, so the largest wavelengths, and we let the system to respond, okay. So we don't know how it is transferred in part to the zero frequency, low frequency modes, and how much is transferred. But what we see that this part of the spectrum remains, in any case, at a very, very low initial amplitude. So there is no any signature of cascade. This is the density spectrum. And more or less, you see that we have exactly the same thing. Okay. Now,
So there is
The-
no permanent excitation of the OK, it's decaying.
exactly. So one possibility could be the low frequency are in some sense when you I mean the ion burst and wave is development of serious development where probably all the high frequency and the low frequency are in some sense coupled together. We don't know. This is a point we have to investigate. Anyway, the idea then was the following. Okay, let's see if there is no transfer at all to the low frequency spectrum, or if it is the Landau damping which inhibits the entropy cascade. So what we've done, we took a very large ratio of the temperature, of the electron temperature with respect to the ion temperature, because we know, I mean, from textbook that in this case, the Landau damping is practically zero, okay? And therefore, we are in the opposite limit with respect to the Bernstein-Landau paradox, okay? So there are no ion acoustic counterparts, so I mean, the waves are there, etc. And again, we start with exactly the same spectrum. This is the electric field spectrum, but then I will show also simulation with an electric field spectrum that decreases initially. I mean, we have used many different initial conditions to be sure that our result. The only point is that, I mean, we do not inject a frequency, we inject a wavelength, okay? The largest, k rho I equal to 1, 2, and 3, okay? And then we let the system respond as it likes, okay? But we do not inject low or high frequency, okay? So in this case, what you see that now the cascade is, and this is the theoretical expectation for the electric fields, okay? So obviously, I mean, it stops where some dissipation on the grid length scale, more or less, where there is some numerical intrinsic numerical dissipation of the algorithm, okay? And if you look at the density spectrum, okay, obviously we obtain exactly the entropy cascade at the expected power law, okay? So,
I'm sorry, I missed the beginning. Is this a spectral code?
no, this is a Vlasov code that use the characteristic approach to advanced distribution function. Means the Vlasov equation is solved by splitting two advection equation, and then we use just an interpolation, but it's not a spectral code.
Can I see those two pictures again with the?
Yes. Yes, I mean the code is tested on, for example, Landau damping, plasma waves, the echo, and then in general it's very accurate on that. This one
Okay, so this is the density, and what is the slope of that line?
is 10/3. Is what is expected from the theory.
And your E spectrum is 4/3.
Is and is exactly, yes, it was here.
But that's automatic, right? Because E is basically D and Y.
Exactly. Yes, that much should
These are
be.
not two independent.
I mean,
variables.
and this is -4/3 over 3.
How about the entity spectrum?
What?
How about the entity spectrum request?
How about the
Entity spectrum.
entropy?
What's the
H spectrum.
H spectrum. The H spectrum. That's the. I mean, these are preliminary results. The problem is that it's not easy to obtain the gyrokinetic distribution function from the Vlasov distribution function. It's very complicated, even numerically. So we are working on that, and we have no, for the moment, information about that. But this is one of the main things that must be done.
Yeah, but at the beginning you discussed the potential energy part can be neglected because of the branch perpendicular wave number.
Yes.
So,
But the potential energy can be neglected because the free energy is dominated by H squared.
yeah.
But the potential tracks H squared by the quasi-neutrality, tracks H by quasi-neutrality condition. So potential is integral of J naught times H,
Yeah, but
roughly speaking.
if,
So
if you take the zero for the moment, okay?
sorry,
Zero for the moment.
it's the zero for the moment. Yes.
So it's totally different from the.
Yeah. No. There is a prediction. So in Tatsuno's paper, there is an H squared. There's an
That's
H spectrum
before the-
which.
Yeah. So
But because it integrates
how
in-
H spectrum look like?
Oh no, we'll sort it out. We don't know.
We don't know. For the moment, we don't know. It's important, but we don't know.
From you.
Correct.
It's just.
But it's not easy to rule it out from the Vlasov distribution function. That's the problem. That's the problem. Okay. Okay, so now the idea was probably there is not enough energy to transfer part of, energy towards the low frequency part, or the amplitude is not large enough such that that part be can cascade in the 60 ion cyclotron period that we use for the simulation. So we increased the amplitude by a factor of 5, and even now a factor of 10. Okay, but more or less the results are confirmed. So if the Landau damping is in the middle, then the entropy cascade develops, and develops faster as expected. But it still do not develop. We still see really nothing concerning. And for this, I will show you a simulation with a different initial spectrum. He now is decreasing in density, and so it's more or less flat in the electric field. So this is still T over Ti equal 1, and as you can see, more or less there is, and the density, same thing, there is no entropy cascade at all. I mean, any sign at even, you see, this is 10 minus 15, 14, 15, etc. So the Vlasov code is very low noise code. So even, I mean, if you don't put any noise, you really stay on 10 minus 15, okay? And you really see that there is no fluctuation there.
So there's, you can work out what the rate of entropy cascade is that is expected. Do you expect any cascade to occur by this time? It's only 12 gyro. In fact, it's only 2 gyro periods, right, divided by 2 pi.
This is, yes, wait, this is not up to, here is up to 27, but we run the code up to, again, up to the same 60 as the previous one. Okay.
But at long wavelengths, there's still a significant signal there.
Yes, yes.
Calculate
Because-
because only at transfer rate. It should be happening because it happened. But it may be that too much is going into first study.
I mean, it seems that
It should be
everything-
constant around the gyro radius, so that these
What?
fast guys go away.
Sorry?
I thought you were going to tell us that you changed the initial conditions since Austria, so that it was constant around the gyro radius,
Uh-huh.
so that we wouldn't have to look at the Bernstein
Ah.
and only look at the low frequency development.
Oh, you mean make a perturbation that doesn't.
Yeah, what Greg was
what
asking.
Greg was
Yes.
No, we haven't done.
No, no, because I mean, to do that, it's quite complicated, because I mean, you have
It's
to,
quite an initial condition.
or either you must add a low frequency forcing. I don't know. It's
No. It should be possible just with the initial.
Yes, or just, I mean, a very precise initial condition. Yes,
It's a given
yes,
perturbation that only depends on the
on the
capacity.
yes, exactly.
And
Exactly.
isotropic perturbation. But
Yes.
that's, isn't it, what perturbation?
No, this is just perturbation on the electric field and the density, yes, in agreement.
If I could get back to a beginner's question. Well, you guys are experts in this. I am not.
Well, you were there before any of us was there.
Similarly will happen to you as well eventually. Something to look forward to. Anyway, just to be sure that I understand, these are unforced, right?
Right.
Yes, just a
So,
decaying.
yeah, so the reason that you expect cascade at all is because of numerical dissipation. Why don't you get thermal equilibrium solutions? out of
That's a
it?
long way in the future, that.
Well,
No,
we don't-
no.
there is dissipation.
This is decaying turbulence.
I understand it's decaying. Well, I
it's-
understand it's decaying, but it's decaying because
There is the numerical
there's numerical
viscosity.
dissipation.
Yes.
And that
yes.
is so strong
Here at
Never
this
expect-
scale, there is some numerical dissipation. in
that
this
so,
scale.
so you never expect to develop a thermal equilibrium solution out of these kinds of simulations.
Right. Tatsuno's code could see, Tatsuno could turn off numerical dissipation because it's spectral.
Did he see, by the way?
And then he could see thermal equilibrium.
Has he ever done it? Well, Greg has a prediction for it, so that could actually be checked.
Can I comment? I mean, I don't know how relevant it is in this case, but sometimes constant flux solutions exist, but they're unphysical. And as an example, I can give you constant flux solutions in force-dissipated Boltzmann equation. This usual classical Boltzmann equation has spheres. It turns out that so formally in infinite inertial range this solution exists, power law solution, and it's been considered in literature for quite a number of papers. But it turns out if you calculate the flux on it, it will be contradicting the field of theory. So namely, the particle flux will be directed toward large momentum, and energy flux will be directed toward low momentum. This means for any finite inertial range, you won't be able to match it to any physical force in dissipation. So I think if we have some sort of cascade predictions, this is something to keep in mind and to be checked. This kind of property.
You see, it's not just a theoretical prediction, right? In numerical simulation, gyrokinetic numerical simulation recovers it. Simulation without damping recovers it. So the issue clearly is the presence of damping.
Well, it's also the initialization.
Or the initialization, yes.
So you said that by this time you should have gotten a cascade based on the amplitude of the perturbation.
Yeah, but it's all gone into
If that amplitude had been in low frequency modes, but instead it's all in high frequency modes.
Yes, but what is interesting is that, if the initial condition goes into the Bernstein waves and not into the zero, then when you have no Landau damping, in principle you also can have no entropy cascade, because this is a completely different response with respect to the previous.
Maybe they just have more time to sort themselves. The low frequencies have more time to sort themselves out when they're not being damped.
The low frequency component is not being damped here, only the high frequency component.
Yeah, but in order to get more low frequency component, you could couple two high frequencies and get low frequency back. But if you manage to damp those high frequencies by then, right?
You see here
You
that
can peak two high frequency waves and get low frequency, so you can get constant input into low frequency. So you can recycle all your initial perturbation into low frequency.
You can if the amplitude is large enough compared to the cyclone frequency.
Yeah.
you see here, for example, we just inhibit the Landau damping, but we solve exactly the same in the ion Bernstein waves. So it's practically the same system of equation. It's the same initialization. We just turn off the Landau damping, okay? And what you see, and we increase the amplitude, so we expect a faster cascade. And indeed, the cascade. No, sorry, this is not the correct way. And indeed, the cascade is much faster. Much faster than before. Okay. So
this is one cyclotron period.
This is 10 cyclotron. Yes, it's one. Yes, two. Yes, two. Yes, with 2 pi is 2 cyclotron periods. So it's very, very fast.
I'm not sure how to interpret.
Yes, we too.
That's too, you're saying this is too fast.
It's very fast.
It's very fast. It's 2 cyclotron periods, but you have a full cascade. But there are still ion Bernstein waves in the system. The only difference is that there is no Landau damping. So it's a puzzle how to.
But it's quite a lot of simplicity. Nonlinear time might actually. I actually think
If your nonlinear time is so fast that it would cause a cascade in 2 cyclotron periods,
Yeah.
gyrokinetics isn't valid.
like all asymptotic theories, gyrokinetics works better than its others.
So now this is this is a regime with beta more or less equal to 1. So in the case of low beta regimes, the situation can be different. But at least for beta equal to 1, I mean for astrophysical application, says that there can be some problems to directly extrapolate the theory on the problem. But I think that the most important point is to try to introduce initial perturbation which is precisely correspond to the zero frequency perturbation and see. But anyway,
well, but it's a complicated question because it has to be zero, it has to be gyrotropic, and it has to depend on the capital R variable,
Yes.
right? Something like that, right?
Yeah.
Because what he is introducing now is basically delta n over n times Maxwell. Right? That's gyrotropic, but it's gyrotropic in little r.
But times e to the I k little r. The
Mm.
problem is you've got to do it in e to the I k
Yeah,
big R.
yeah.
but anyway, what is very strange is that if, in any case, okay, we have in this case where there is no depth, okay, you see that in principle you can think that your initial perturbation has, for example, a component which is ion burst and waves, which is the majority, and the small component. But the small component, for example, starting from here, even very, very small, should make on some, at large amplitude, some cascade we should see. But we see really, really nothing on that part of the spectrum. Really nothing. Yes.
Is it possible to make a theoretical prediction of what the density in an electric field should do if you assume that they're just passively affected by the large amplitude, high frequency stuff, or just scattered off, they're just scattered by it? And then, is there some quirk that it turns out to be the same scale? I mean, are we?
That's the exercise for tomorrow.
Yes.
Sure, I'm sure it's possible.
Yeah.
Yeah.
Okay, so this is the obviously the density show exactly the same thing with the expected power law, and this is the 2D spectrum. I don't want to take more time because I think we are later. So one important thing for the future is to look at the velocity space structure, because our impression is that the velocity space space is, I mean, the structure are not so fine as expected from the theory, because we vary the resolution in velocity and there was no significant important changes. On the other hand, if you vary the spatial resolution, this obviously change completely the possibility to make a larger cascade. But at the moment we had any signature about the role of the velocity fluctuations
Yeah, but
at the moment.
this was true for Tatsuno as well. When he tried, he always needed more resolution in real space than in velocity space.
Yes, so there means at least some coefficient.
And even at kind of
About.
Gaussianly resolved velocity space, he would still get the right scalings in K space, but not in V space.
Maybe instead, with maybe a simple diagnostic, you could take your existing results and then put those in the big R coordinates, multiply by e to the I k big R, and look at the velocity space then. You might be getting more structure,
Yeah.
which would be what Alex's theory just talked
For
about,
example.
rather than.
I mean,
Yeah,
and
we
yes, that's
Then the
possible.
spatial is going to get mixed in. It'll have more structure.
That's possible. I mean, at the moment, what we have done, we have varied significantly the resolution in velocity phase space, and it's not has no important effects on the space cascade. But I mean, it's a work in progress, and
But
what
you can't
is-
make it
is-
zero, right? You
Yes.
can't make it no resolution.
Yes, I mean, it can be then that there is a coefficient.
With
so
only
you-
2 points in velocity space, it doesn't work.
And you're messing up my talk when you say that.
That's right. Bill's talk will be about how it works with 2 points. in velocity
2
space.
points. But I think that the most interesting point is try to understand how it's possible to excite such low frequency modes even when the electron temperature is of the order of the ion temperature, if it is. I mean.
One may have to drive the cascade.
What's the prediction for phi squared again? Goes like,
10
phi squared goes like
well, spectrum of
Okay, that's it.